Hey there. Welcome to our channel. We're so glad you're here. Please like, share, and subscribe to join us for awesome content. Also share this video with your family and friends. Let's get started. Imagine for a moment that the universe has two sets of rules. Asterisk asterisk, the first is the one you know, the one that keeps your feet on the ground, the sun in the sky, the clock ticking forward without hesitation. Here, cause and effect move like steady hands, building bridges, launching rockets, measuring time in unshakable beats. This is the world of classical physics, where things are solid, predictable, obedient. But beneath it, woven into the fabric of every atom, every flicker of light, there is another rulebook. One where particles forget to be particles, where an electron is not just here or there, but both, neither, somewhere in between until you ask it to choose, where reality itself seems to hesitate, as if deciding what to be. This is the quantum realm, and it does not play by the rules you were taught. The stage of the very small, think of a stage. On it, a single actor performs a monologue, clear, audible, moving from one line to the next without pause. This is how classical physics behaves. Orderly, direct, one thing after another. Now imagine that same actor splits into two, then four, then 1,000. Each version speaks a different line in a different tone all at once. Yet somehow, impossibly, the audience hears only one coherent story. This is how quantum particles behave. They exist in superposition, a delicate state of all possible versions at once, until something, a measurement, an observation, the universe itself, asks them to settle into a single answer. It's as if reality, at its core, is a conversation between certainty and possibility. The fading edge of certainty, you might wonder. If the quantum world is so strange, why don't we see it? Why don't cats, cars, coffee cups blur into multiple versions of themselves? The answer lies in scale. Quantum weirdness thrives in the realm of the very small, atoms, electrons, photons, where particles are so light, so insubstantial, that they barely interact with the world around them. But as objects grow larger, as trillions of atoms clump together, their quantum whispers are drowned out by the noise of ordinary physics. Like a single voice lost in a choir, the strange rules fade into the background. And yet, they never disappear. A game without a referee in the classical world. If you throw a ball, its path is decided the moment it leaves your hand. But in the quantum world, the ball could go left, right, up, down, all at once until it lands. Only then does it pick a single trajectory. This isn't just theory. Experiments have caught particles red-handed in this act of indecision. In the famous double-slit experiment, electrons fired one at a time through two narrow gaps don't just go through one or the other. They go through both, interfering with themselves like ripples in a pond. It's as if each particle is a wave of potential, collapsing into a single point only when observed. Einstein struggled with this. He insisted that reality should be definite, independent of our looking. But the universe, it seems, disagrees. The rules beneath the rules asterisk asterisk, so what are these hidden quantum laws? They are mathematics that describe probabilities, not certainties. They say that particles have no definite position until measured, only a likelihood of being here or there. They allow for entanglement, where two particles, once linked, mirror each other instantly across any distance, as if space means nothing to them. And most strangely of all, they suggest that the act of observation, of asking a question, changes the answer. It's as if the universe, at its heart, is not a machine, but a conversation. A softer kind of logic, you might find this unsettling. After all, we are creatures of certainty. We build clocks, maps, plans, tools that assume the world follows neat, predictable rules. But the quantum realm does not care for our need for order. It is a place where either slash or becomes both slash and, where particles tunnel through walls, where time itself can bend. It is not chaos, though. It is a different kind of order, one that runs on probabilities, on waves, on questions rather than answers. And perhaps, in its own way, it is beautiful. As you drift deeper into this hidden rulebook, you begin to wonder, if particles can be in two places at once, what else might be possible? And just like that, the idea of a single, solid reality begins to soften at the edges, like sand giving way to water, like twilight fading into night. The bit that learned to dream. Imagine a light switch. It has two states, on or off, 1 or 0, yes or no. This binary certainty is the foundation of every classical computer, the unshakable logic that built the digital age. Billions of tiny switches, flipping in perfect unison, processing the world in clean, decisive steps. But now, imagine a switch that refuses to choose. One that hovers between on and off, humming with the potential of both. A switch that exists in a state of maybe. This is the heart of a quantum bit, the qubit, and it does not obey. The weight of a maybe. A classical bit is like a coin resting on a table. Heads or tails, settled, final. But a qubit is a coin still spinning in midair, not just heads or tails but both, neither, all the possibilities at once. It is a breath held between inhalation and exhalation. A dandelion seed suspended in the wind, refusing to land. This is superposition, the qubit's ability to hold multiple states simultaneously. And it changes everything. Because while a classical computer must explore one path at a time, like a traveler checking every door in a hallway, a quantum computer can step into all doors at once. It doesn't just calculate answers. It lingers in the space between question and solution, testing every possibility in parallel. The fragile art of holding still, but there's a catch. A qubit's power is also its fragility. The moment you measure it, the moment you ask it to declare itself, it collapses into a single state, 1 or 0. The maybe becomes a must. The dream becomes a fact. Keeping qubits in superposition is like trying to hold a soap bubble on your fingertip. The slightest disturbance, a stray photon, a vibration, even the warmth of the room, can burst the illusion. That's why quantum computers live in cryogenic chambers, shielded from the world's noise, suspended in temperatures colder than deep space. They are machines built to cradle uncertainty. The language of spins and stars. How does a qubit physically hold this delicate state? Some are made from electrons, their spin acting like a tiny compass needle pointing both north and south at once. Others are fashioned from loops of superconducting wire, where current flows clockwise and counterclockwise simultaneously, a paradox made real. The most poetic of all might be trapped ions, single atoms suspended in electromagnetic fields, their energy levels humming like tuning forks struck at multiple frequencies. These are not just engineering choices. They are translations, ways of forcing the quantum world to speak in a language we can almost understand. A new kind of logic. Classical computers are like librarians. Meticulous, exact, following instructions step by step. Quantum computers are like poets. Intuitive, fluid, holding contradictions without breaking. This isn't about raw speed. It's about a different way of thinking. A classical computer solving a maze checks every dead end one by one. A quantum computer feels the maze, all paths at once, and leans toward the exit. It doesn't brute force its way through problems. It dances with them. The limits of dreams. Yet, for all their promise, quantum computers are not omnipotent. They won't replace your laptop. They excel only at specific tasks, simulating molecules, cracking certain codes, optimizing labyrinthine systems, where their parallel dreaming offers an edge. For everything else, the old, reliable bits still reign. But perhaps that's the lesson. The universe itself runs on both rules, the certain and the uncertain, the classical and the quantum. And in that balance, there is magic. As you ponder the qubit's defiance of either slash or, a deeper question lingers. What happens when these dreaming bits intertwine? When one qubit's fate becomes bound to another, across space and time? The answer is stranger than fiction. It's a phenomenon so puzzling. Even Einstein called it spooky. Picture a cat. Not just any cat. A cat curled inside a sealed box, where no light enters, no sound escapes. In this box rests a tiny, treacherous device, a radioactive atom that may or may not decay in the next hour. Loving this? Hit that subscribe button to keep up with our videos. Also share this video with your family and friends. If it decays, a hammer shatters a vial of poison. If it doesn't, the cat lives. But here's the quantum twist. Until someone opens the box, the atom exists in superposition, both decayed and not decayed at once. And so, by extension, does the cat. Alive and dead. Asleep and not asleep. A purr and a silence, existing simultaneously. This is Schrödinger's famous paradox, not a real experiment, but a poetic protest against the absurdity of quantum theory. And yet, in its strangeness, it holds a profound truth. Reality may hesitate until observed. The weight of a peak, why does this matter? Because it forces us to ask, when does possibility become fact? In our everyday world, things seem solid whether we look at them or not. The moon doesn't vanish when you glance away. But in the quantum realm, particles do seem to wait for observation before choosing their state. An electron isn't here or there until measured. A photon isn't a wave or particle until detected. The cat is a metaphor for this quantum indecision, scaled up to something we can feel. It's unsettling because it suggests that reality, at its core, is fluid, that the universe might be a tapestry of maybes, stitched into certainty only when a conscious mind pulls the thread. The dreaming universe, some interpretations go further. The many worlds theory suggests the cat never chooses. Instead, the universe splits. In one branch it lives. In another it dies. Both outcomes are real, just separate. Others argue that consciousness itself causes the collapse, that the act of seeing crystallizes reality. But the most pragmatic view? The observation doesn't need a human. Any interaction, a photon bouncing off the atom, the poison vial jostling, counts as a measurement. The universe is always peeking at itself. Quantum sleep, there's a reason this thought experiment feels like a lullaby. It mirrors the moment between wakefulness and sleep, when you're neither fully here nor gone, when the world softens into ambiguity. The cat in the machine. Modern physicists have created real versions of Schrödinger's cat. Not with felines, but with tiny drums, superconductors, even viruses placed in superposition. These experiments prove quantum effects can scale up, blurring the line between the tiny and the tangible. Yet the original paradox endures because it asks the deeper question. Where does the quantum world end and the classical world begin? Is there a size limit to superposition, a temperature? Or is everything, in principle, capable of quantum weirdness, if only we could isolate it well enough? The comfort of unknowing, you might crave a clear answer. Is the cat alive or not? But quantum mechanics resolutions. It lives in the and, not the or. As you drift towards sleep, the box remains unopened. The cat's soft breaths, or are they yours? Hover between certainty and dream, and you wonder, if observation shapes reality, what happens when no one is looking at all? The spooky threads of entanglement. Picture two coins. You flip them at the same time, miles apart. One lands heads up. Instantly, faster than light could travel between them, the other snaps to tails. Not random chance. Not a trick. A perfect, instantaneous mirroring, as if the coins share a single mind. This is quantum entanglement. A bond so profound it defies locality. The classical notion that objects are only influenced by their immediate surroundings. Two entangled particles, no matter how far separated, remain mysteriously linked. Measure one and its partner knows, adjusting its properties in perfect opposition. Einstein hated this idea. He called it Spukhaft Fernwirkung, spooky action at a distance. To him, it violated relativity's sacred rule. Nothing travels faster than light. But experiment after experiment has proven entanglement real. The universe, it seems, keeps secrets even from Einstein. The dance of opposites. How does entanglement work? Imagine a pair of gloves. You take the left glove to Paris, the right to Tokyo without peeking. Open the Paris box. It's left-handed. Instantly, you know Tokyo holds the right. No signal needed. The information was always in the correlation. But quantum gloves are stranger. Until observed, each glove is both left and right. Only when you check one does it choose, forcing its twin into the opposite state, even if that requires flipping faster than light could bridge the gap. This isn't about hidden instructions. It's as if the gloves weren't separate at all, but two expressions of a single quantum essence. The fabric of reality. Entanglement suggests something radical. Space might be an illusion. At the quantum level, distance loses meaning. Two electrons born together remain bound whether they're nanometers or light-years apart. Their connection isn't through space. It's underneath space, woven into reality's foundation. Think of it like a puppet show. We see separate puppets moving on stage, unaware their strings all tie to the same hidden hand. Entangled particles are those puppets, appearing independent yet fundamentally one. The comfort of non-locality, there's something oddly soothing about this. In a world where we often feel isolated, separated by screens, time zones, misunderstandings, quantum mechanics whispers. Appearances deceive. Things that seem apart might be intimately joined at levels we can't see. Entanglement proves connection doesn't require proximity. Some bonds bypass distance entirely. The quantum net scientists now entangle not just particles, but entire clouds of atoms. They've sent entangled photons through fiber optics, even to satellites, testing if the link survives cosmic distances. It does. Some theorize the early universe was a hot soup of superentangled particles. As it expanded, these connections stretched but never broke. That means your body, this page, might still share faint quantum ties with distant stars. The night sky suddenly seems less empty. The limits of spookiness. Can we use entanglement to communicate faster than light? Sadly, no. The correlation only appears after comparing measurements, which requires classical signals, limited by light speed. Entanglement is like two people opening sealed letters miles apart. Each finds random gibberish until they meet to decode the pattern. But it enables quantum teleportation, transferring a particle's state to another location by exploiting entanglement. Not Star Trek beaming, but proof that information can leap between points without crossing the space between. A thread through time. Most hauntingly, entanglement might transcend time too. Recent experiments suggest particles can become entangled after they've been measured, as if the link reaches backward through causality. It's as though quantum connections exist outside our usual flow of past, present, future. This hints at a deeper layer of reality, one where separation is a surface feature, and all things are fundamentally close. As you stare at the night sky, consider, those pinpricks of light might still be quantum knitted to your bones. And if particles can whisper across the void, what other invisible threads might bind us? The quantum loom, weaving parallel worlds. Close your eyes. Picture a moment, a single, ordinary moment where a choice hovered before you. Perhaps it was this morning. Tea or coffee, left turn or right, a word spoken or withheld. In your memory, only one path was taken. But quantum mechanics whispers a secret. Every possibility happened. Somewhere, in some version of reality, each choice unfolded. The universe, it seems, cannot bear to let a maybe go to waste. This is the many worlds interpretation, the idea that reality is not a single thread, but an endlessly branching tapestry. And at its heart lies a question. What if you are not just one reader of this story, but many? The forking path, the mathematics of quantum mechanics are clear. When a particle exists in superposition, here and there, spinning up and down, its multiple states don't collapse into one upon observation. Instead, the universe splits. One version observes the particle here, another, there. Scale this up. Every quantum event, every flickering atom, every qubit's hesitation, becomes a new branch. A cosmic kaleidoscope where the quantum computer's secret. This is why quantum computers are so powerful. A classical computer must plod through calculations one by one, like a librarian checking each shelf. But a quantum computer exploits superposition to live in all possibilities at once. When you ask it to solve a maze, it doesn't try every path sequentially. It becomes 1,000 versions of itself, each exploring a different route simultaneously. In essence, it harnesses the many worlds theory as a tool. It lets parallel universes do the work. The you that you didn't become. These aren't just fantasies. In the many worlds view, they're as real as the version you're living now. The quantum ripples that spawn them are no different from the ones that keep electrons buzzing in your bones. You might wonder, do those other yous feel as real as you do now? The answer is almost certainly yes. The comfort of branching at first, this seems lonely, an infinity of roads not taken. But there's solace in it too. Every regret is soothed by knowing it was also avoided. Every tragedy is balanced by versions where it didn't occur. The universe, in its boundless generosity, refuses to let any possibility fade unrealized. It's like reading a choose-your-own-adventure book where every choice is followed to its ending. No story is lost. All are cherished. The stitch in time. Remarkably, this isn't pure philosophy. Quantum decoherence, the process by which quantum probabilities collapse into classical certainty, aligns neatly with many worlds. What we perceive as collapse may just be our awareness settling onto one branch, while others spin onward unseen. Experiments with delayed choice and quantum erasers hint that reality might decide its past based on present observations, as if the tapestry rewoven its pattern to match the thread you're holding. Dreaming in parallel **** as you drift towards sleep tonight. Consider. Somewhere, a version of you is already asleep. Another is reading this sentence twice. Another closed the book pages ago. Yet here you are, this particular you, this specific thread in the grand weave, feeling the weight of eyelids, the slow surrender to dreams. And perhaps, in the quantum haze between waking and sleep, those other versions don't seem so distant after all. The pillow cradles your head as the boundaries of self grow softly porous. And you wonder, as sleep pulls you under, which dreams are yours, and which belong to the you that chose differently. The fragile magic of superposition ***. Imagine holding a snowflake in your palm. For one fragile moment, it exists in perfect superposition, both melting and not melting, water and ice, shape and puddle. Then, inevitably, the warmth of your skin decides its fate. The in-between state collapses. It becomes either or, never both. This is the essence of quantum superposition and its greatest vulnerability. The universe permits particles to exist in multiple states at once, but only if we don't look too closely. Only if the world doesn't nudge them toward certainty. This isn't just theoretical. We've photographed particles behaving as probability waves, fuzzy clouds of could be, that only solidify into is when measured. The universe, it seems, prefers to dream until forced awake. The noise that breaks the spell ***, but superposition is easily shattered. The quantum realm is a hall of mirrors where this is decoherence, the process by which quantum magic leaks into the classical world. Like a dream upon waking, superposition fades when exposed to its environment. The snowflake melts. The dancer falls. The coldest place in the universe ***. Here, qubits can spin their quantum dreams for milliseconds, sometimes even minutes before reality intrudes. It's the closest we've come to stopping time. The butterfly effect, quantum style ***, the sensitivity is unimaginable. In some quantum computers, it's as if the quantum world exists one breath away from dissolving. A soap bubble universe where every touch leaves fingerprints. Why fragility matters ***. This isn't just engineering frustration. The delicacy tells us something profound. Reality is a conversation between observer and observed. The quantum realm remains fluid only when undisturbed. The moment something, a detector, a dust particle, the universe itself, asks for definite answers, the magic collapses into mundane certainty. The beauty of impermanence ***. Superposition reminds us that some wonders can't be preserved, only witnessed briefly before they transform into something else. As your breathing slows, the boundaries between thought and dream grow porous. And you wonder, in that last moment of wakefulness, are we two fragile superpositions? Brief constellations of atoms that only seem solid until the universe turns its gaze our way. The guardians of quantum secrets ***. There is a letter that cannot be opened. Not because it lacks a seal or key, but because the very laws of physics guard its contents. The moment an unwelcome eye tries to read it, the words dissolve, like moonlight scattering on disturbed water. This is the promise of quantum cryptography, where secrets are woven into particles themselves, protected by the universe's fundamental rules. For centuries, codes relied on mathematics so complex that cracking them took years. But quantum encryption is different. It doesn't trust in complexity. It trusts in physics, in the behavior of photons that refuse to be copied, in entangled particles that betray eavesdroppers, in the fragile magic of superposition that collapses when observed. This isn't just better security. This is security written into the fabric of reality. The key made of light ***. Imagine Alice wants to send Bob a secret. In classical cryptography, she might use a public key, a mathematical lock anyone can see but only Bob can open. Given enough time and computing power, though, any lock can be picked. But in quantum cryptography, Alice sends her key encoded in individual photons. Each photon's polarization, vertical, horizontal, diagonal, represents a bit of information. Here's the magic. Any attempt to measure these photons changes them. Heisenberg's uncertainty principle. Entangled photon pairs instantly reveal eavesdropping. The act of reading the key destroys the original. It's like sealing a message in ice that melts if touched. The universe itself becomes the courier and the bouncer. The eavesdropper's dilemma ***. Let's say Eve tries to intercept Alice's quantum key. To read the photons, Eve must measure them. But quantum measurement is destructive, like trying to learn a snowflake's pattern by catching it in your hand. The very act of looking alters what's seen. Alice and Bob will immediately notice. Error rates spike in their transmission, entangled particles stop mirroring perfectly, the key becomes noisy. With interference, they discard the compromised key and start over. No brute force attack can bypass this. Either the key arrives pristine or not at all. The unhackable network ***. Since the 1980s, quantum key distribution, QKD, has evolved from theory to reality. 2004, first bank transfer secured by quantum cryptography. 2017, China's Michia satellite sends quantum keys across continents. 2023, quantum-secured voting systems tested in Switzerland. The vulnerabilities? Not in the physics, but in the imperfect human engineering around it. The lasers that misfire, the fiber optics that scatter light. The universe's lock is perfect. Our doorknobs still squeak. The quantum internet dawns ***. Future quantum networks might use repeaters that entangle photons across global distances without measuring them, like whispering a secret through a chain of friends where no one ever hears the full message. In this coming age, medical records could be sealed in quantum certainty. Elections might have mathematically verifiable integrity. Nuclear launch codes could become truly unstealable, all guarded by particles that refuse to betray their secrets. The paradox of quantum privacy ***. Yet there's an irony here. Quantum mechanics birthed this perfect secrecy, but may also destroy current encryption. Shor's algorithm, run on a powerful enough quantum computer, could crack today's digital locks in minutes. So we race, building quantum-safe cryptography even as we harness quantum vulnerability. It's an arms race where both weapons and shields come from the same strange quantum rules. The oldest secret keeper ***. Perhaps this shouldn't surprise us. Nature has used quantum encryption for eons. Photosynthesis relies on quantum coherence. Bird navigation uses entangled radical pairs. Even our sense of smell may exploit quantum tunneling. The universe has always known how to hide secrets in plain sight. In the flutter of a photon, the spin of an electron, the delicate dance of particles that vanish when stared at too hard. ***. As you drift towards sleep, the night outside hums with photons carrying secrets, some earthly, some cosmic. And you wonder, what other locks might the universe be hiding in its quantum pockets, waiting for us to learn how to ask? The noise beneath the quantum hush ***. There is a room in Oxford so quiet it echoes with the absence of sound. Inside, suspended in a bath of liquid helium colder than deep space, a quantum processor hums its fragile calculations. The surrounding machinery works tirelessly to maintain this artificial winter, blocking magnetic fields, absorbing vibrations, shielding against even the whisper of cosmic rays. Here, in this engineered silence, qubits can spin their quantum dreams for precious microseconds before the noise of existence shatters them. This is the dirty secret of quantum computing. The universe itself is too loud. The symphony of interference ***. A perfect qubit is like a single pure note held in a cathedral. But reality intrudes, thermal noise, atoms jostling at room temperature, a riotous mosh pit to qubits, electromagnetic whispers, Wi-Fi signals, Earth's magnetic field, even distant supernovae decoherence. The quantum version of a record scratch, superposition collapsing into noise. Each disturbance is trivial to humans. To a qubit, they're earthquakes. A single photon at the wrong frequency can corrupt an entire calculation. The art of quantum silence ***. To combat this, engineers have become masters of stillness. 1. Cryogenic enclosures. Keeping qubits near absolute zero, minus 273 degrees Celsius, where atomic motion nearly stops. 2. Vibration platforms. Floating entire labs on pneumatic springs to cancel footsteps. 3. Muon shields. Layers of lead and copper to block cosmic particles. 4. Dark architectures. Qubit designs that naturally reject certain errors. It's like trying to hear a snowflake land during a hurricane. The harder we listen, the more we must silence the world. The paradox of control ***. Here lies the irony. To harness quantum weirdness, that ethereal, probabilistic magic, we must exert near-total classical control. We trap particles in electromagnetic cages, freeze them in cryogenic prisons, isolate them in vacuum chambers. We force the quantum world to behave by removing every possible alternative. It's as if the universe resists being used this way, as if quantum phenomena were wild horses that only run when not directly observed. The ghosts in the machine ***, even our best efforts leak noise. Tunneling errors. Qubits slipping through barriers like ghosts through walls. Crosstalk. Qubits whispering to neighbors despite insulation material defects. Imperfections in superconducting metals singing off-key. Current quantum error correction requires 1,000 physical qubits to protect one logical qubit. A cosmic game of whack-a-mole where the hammers are lasers and the moles are entropy itself. The lesson of fragility ***, perhaps there's wisdom here. The same sensitivity that makes qubits so easily disturbed also gives them power. A classical bit ignores the universe, a qubit listens to it. To every vibration, every photon, every whisper of interference. This isn't weakness. It's an acute awareness, a reminder that nothing truly exists in isolation. The search for quiet ***, new approaches emerge. Topological qubits. Particles so stable they're theorized to exist in 2D planes. Phononic engineering. Sculpting materials that absorb specific vibrations. Natural qubits. Using diamonds with built-in nitrogen vacancies, each tries to outsmart noise in different ways, not by creating perfect silence, but by teaching qubits to dance with the chaos. As your breathing slows, the ordinary noises of night, a distant car, the house settling, feel suddenly immense, and you wonder, if a qubit requires such perfect silence to dream, what quantum possibilities might be unfolding in the hidden quiet of your own cells? The alchemists of the impossible ***, there exists a molecule that could cure Alzheimer's. It waits, hidden among 10 to the power of 60 possible molecular combinations, more variants than there are stars in the observable universe. Classical computers groan at such numbers. They would require millennia to check each possibility. But a quantum computer, dancing through all probabilities simultaneously, might find it in hours. This is the alchemy quantum computing promises. Not turning lead into gold, but transforming impossible into inevitable. Where once we could only discover what nature revealed, soon we may design reality at its most fundamental level. The library of all possible medicines ***, imagine mapping every potential drug interaction like constellations. Protein folding. Quantum simulations untangling Alzheimer's plaques and cancerous knots. Catalyst design. Clean fertilizers that don't choke oceans with dead zones. Personalized medicine. Drugs tailored to your quantum biological fingerprint. Current supercomputers simulate molecular interactions atom by painstaking atom. Quantum machines will play entire chemical symphonies at once, hearing not just the notes but the harmonies between them. Materials from dreams ***, some theoretical materials defy classical calculation. Room temperature superconductors that could levitate trains and revolutionize energy grids. Metamaterials bending light like Superman's crystals. Self-healing polymers mimicking quantum tunneling in spider silk. These aren't incremental improvements. They're substances that should be impossible under classical physics. Yet quantum mechanics whispers they might exist. Soon we'll have the tools to listen. The carbon revolution ***, consider graphene, a sheet of carbon 1 atom thick, stronger than steel. It was theorized decades before isolation. Quantum computing could accelerate such discoveries. 1. Predicting stability of exotic material phases. 2. Simulating quantum dots for ultra-efficient solar panels. 3. Designing topological insulators where electricity flows only along edges. The next industrial revolution won't be about bigger factories, but deeper physics. The limits of this magic yet quantum computers won't solve everything. They're terrible at spreadsheets and email. Most everyday tasks remain better suited to classical chips. Their true power lies in reconfiguring reality's building blocks. This isn't about speed. It's about accessing solutions that literally couldn't be calculated before. The ethics of alchemy with such power comes profound responsibility. Who controls weather-altering atmospheric catalysts? How do we regulate quantum-designed neuropharmaceuticals? Can we prevent algorithmic arms races in material science? We're not just building better tools, we're rewriting the rules of invention itself. The quietest revolution unlike the steam engine or silicon chip, quantum advances may unfold invisibly. No roaring factories, just cryogenic labs humming near absolute zero, no consumer gadgets, but fundamentally better batteries, medicines, materials no obvious before and after. Just a slow realization that yesterday's impossibilities now work. The greatest changes often slip into our lives unnoticed. As sleep pulls at your eyelids, the boundaries between possible and impossible blur. And you wonder, as consciousness fades, what other impossibilities are waiting patiently in the quantum shadows, simply needing us to learn how to look. The bedtime of certainty there comes a moment each night when you stop resisting sleep. Your thoughts grow soft at the edges. The bed feels heavier beneath you. The line between here and there, now and then, begins to blur, not unlike an electron relaxing into superposition, no longer forced to choose between states. This is the quantum realm of the mind, a twilight where contradictions coexist, where certainty dissolves into something more fluid and forgiving. For all its complexity, quantum mechanics ultimately teaches us this simple truth. The universe is far less stubborn than we imagined. Things can be both. Rules can bend. Observation changes what's observed. As you hover in this liminal space, you realize the quantum world isn't some distant strangeness. It's been here all along, humming beneath the surface of your ordinary moments. The certainty we outgrew for centuries, we believed in a clockwork universe. Predictable, mechanical, unwavering, but quantum physics replaced Newton's gears with something more organic, a reality that breathes, fluctuates, responds. The comforting solidity of either or gave way to the expansive both and. We learned that light is both wave and particle. Cats in boxes are, theoretically, alive, and dead particles communicate faster than light. Should allow the world became less certain, but somehow more alive. The wisdom of uncertainty there's a quiet liberation in quantum thinking. Mistakes aren't failures, they're alternate paths explored. Contradictions don't always need resolving. Not knowing becomes its own kind of knowing. You've felt this before. In the creative haze between idea and execution, during conversations where meaning flows beneath words at twilight, when the world hesitates between day and night, quantum physics simply gives this experience a name. Superposition of mind. The particles of you consider that your body right now hosts, electrons that were once inside stars, atoms that may have belonged to dinosaurs or daisies, quantum vibrations in your cells, microtubules. You are, literally, a walking quantum phenomenon, as transient and entangled as any qubit. The same rules governing particles in labs govern the electricity in your neurons, the photosynthesis in the plants outside your window, the starlight entering your pupils as you glance toward the night. The measurement problem of consciousness here lies the final mystery. When you fall asleep tonight, who observes you? Does your consciousness collapse reality's possibilities into a single experience? Or do all possible dreams play out across the multiverse? Quantum physics offers no definitive answer, only the reassurance that uncertainty is fundamental, not failure. The pillow accepts the weight of your head. The blanket's embrace feels both here and not here. As you finally surrender to sleep, you realize you're not falling into darkness, you're entering superposition. And somewhere, in some version of this moment, you're already dreaming. Thanks for watching. Please subscribe, like, and share. See you next time.